A relative compression test is a great way to check the compression values of each cylinder without the time-consuming task of removing the spark plugs or glow plugs from a modern engine. If we're diagnosing a misfire or low power concern, we can determine very quickly if we have a cylinder pressure loss occurring. The only tools we need for this job is an oscilloscope and a current clamp. A relative compression test uses the engine starter motor's current draw to determine the comparative compression values of all cylinders in the engine. The energy or current draw needed to turn over an engine while each cylinder is on its compression stroke can be measured. An indication of the pressure value within each cylinder can be displayed as a waveform. All we need to do is interpret that waveform to determine if a problem exists. Sounds simple? Well, it really is. Before performing a relative compression test on an engine, we need to prevent it from starting during crank. This is no different from when we perform a mechanical compression test. The best way to disable the engine is to remove the fuel source. This is as easy as removing a fuel pump fuse or relay, and then running the engine until it stops. Next, we'll connect the current clamp to either the battery positive or negative cable. Make sure the clamp is facing in the correct direction, as indicated. If we don't do this, the trace will be inverted when displayed on the scope. Connect the clamp to the first channel and then power the scope up. Most petrol or gasoline powered vehicles will draw around 400 amps on initial crank, with diesels slightly higher. This is a low amp clamp, which has two maximum settings, 20 amps and 60 amps, which is a little low for our test. But we can adjust for this in the scope settings. With this in mind, I've selected the 20 amp probe with a 20 amp scale, so that the trace can be displayed on the screen. If you're using a different scope or clamp, just select the scale that suits the vehicle needs. While we're here, I've also selected a 5-second time base, which works well for this tool. Again, you may need to adjust it either way for your particular scope and the engine cranking speed. Once the scope values are set, we can zero the clamp. Now, hold the throttle wide open to allow maximum air to enter the cylinders, and then crank the engine for about 5 seconds. Let's take a look at the results. The initial peak we see is the current required to overcome stationary engine friction and begin crankshaft rotation. Once the engine is rotating, the current value drops. We can compare each cylinder's pressure by monitoring the current required to push each piston through its compression stroke. The higher the compression, the higher the current draw on the starter. With the value of each peak displayed on the scope, a determination of the engine's relative compression can be made. What we want to see is that all peaks and troughs are equal, indicating even compression pressure on each cylinder. A loss of compression in any cylinder is seen as a missing or much lower peak than the others. If we see a low compression value, we can easily identify which cylinder is causing the problem. Connect a second cable to the next free channel on the scope, and then back probe either cylinder 1 ignition coil trigger, cylinder 1 fuel injector, or use a secondary ignition clamp attached to a spark plug lead. If we're checking a common rail diesel engine, number 1 fuel injector is the choice. This is known as our sync signal. If we repeat the test with the second waveform overlaid, we can see which peak is cylinder 1 compression. All we need now is the vehicle's firing order to identify which cylinder is at fault. If we see low compression or low current draw across all cylinders, we need to think about what may cause this before condemning the engine. This could simply be poor battery condition, the viscosity of the engine oil during the test, or incorrect valve timing due to belt or chain issues. Starter motor current draw will also be different between 4, 6 and 8-cylinder gasoline and diesel engines. It's much easier if we know what the current draw should be for a particular engine in good mechanical condition. The best way is to develop a waveform library that can be referenced during a relative compression test. We can now take the results to the customer and justify the necessary time and expense to remove the spark plugs, glow plugs, or injectors to perform a cylinder leak down test and correctly diagnose the fault. As always, keep training. Thanks for watching.